Hello.
Hello, hello.
Hello.
How is everyone?
Doing well, thank you.
Good.
Yeah, doing well.
Glad to hear it. So, I was going to speak a little bit about cut elimination. Just looking for a paper that I have somewhere here. Let's see. Here it is. Yeah, got it. Okay. And one other piece. Here we go. So Mike and I have been looking at the categorical interpretation of the proof theory for ladle. And do a quick screen share. So in general, when you're doing a categorical interpretation, you need to come up with what the objects are, what the morphisms are, and what the notion of composition is. And here, what we're suggesting is that the objects are types, and the morphisms are witnesses of those types, and that the notion of composition is going to be cut. So when we say cut, we mean rules of this form. So here's one. So I've got gamma thinks that T prime is of tau perp, and delta thinks that T is of type tau. Then if you glue gamma and delta together, then you get the K, which is whatever the red X formation constructor is. You take K of T prime and T, and you supply it some gas, and that will be R of the identity for K. So essentially what we're saying is, even though there's still maybe lots of compute that goes on in here, at the end of the day, you won't be able to see it. You'll stop. You'll get down to something that's the identity. So that's kind of the idea, and there are variations of that. And when we get cut elimination, which is so the idea is that all proofs that use the cut rule can be turned into proofs that don't use the cut rule simply by running the computation until it's done, or you're out of gas, which is the same as it's done. And so that's a little that's a nice result, but what it does is it calls into question sort of what the notion of composition is in the category, and the thought, as we have been pursuing it for some time now, is that we follow linear logic framework as much as possible. So it turns out that the geometry of interaction is in fact the dominant paradigm that we're following. So our notion then is going to be guided by this trace monoidal interpretation. And it turns out that see if I can find the composition here. Actually, I think that's sort of interesting. Just looking for the notion of composition. So they give lots of examples in this paper, and the examples are absolutely worth taking a look at.
Can we say that cut elimination is like normalization, that we want to find?
Yes, that's exactly the idea.
And this resource is, so maybe we don't have, maybe we still have Redex, but because we don't have a resource, we cannot normalize it further. And so we can say that this is like a normal form with these resources.
That's right. That's right. And in fact, it's exactly what we're. So here's a pictorial representation of the execution formula. Essentially, what you get is you're going to come in with some input, and if you're already at the base case, you go straight out. But if you're not at the base case, so you have some gas, then you've got a K, then you run to completion. You go around the loop with Ks that have gas, and then you're out of gas, and now you can come out. So that's the basic idea for how how we will interpret the execution formula in this context, and what cut elimination means. The next thing that we'll be going after is the interpretation of the trace. Right. So the trace will be here's the requirements for the trace right here. So it's a tensor. So essentially what you've got is you've got some tensorial gadget. And so in that case, it's the K is the tensor, right? And then you tensor with some U, and then you trace it out. You trace out the U. So you have X tensor U and Y tensor U, and then you can go down to just the X and the Y. So you're getting rid of this bit here. And there are some things that have to hold. So for example, if you trace out U over F and you compose that with G, that's the same as composing G with the, or tensoring G with the unit for U, and composing that with F and then tracing over the whole thing. And on the left-hand side as well.
Can you say more about tracing out the U? What does it mean, and what is U?
So think about U, like if you've ever written a fold in functional programming, right? So when you write a fold, like a fold left, you give it an accumulator and a seed. And when you're done running the fold, the accumulator parameter is gone.
Yes.
Right? Okay.
Accumulator is the result, right?
Yeah, exactly. So U is like the accumulator. right? So we're starting with something that's X tensor U and Y tensor U, and we get rid of the U part, and we just have this. So this U is the accumulator parameter.
Oh, I see.
Yeah.
Okay.
So when we trace it out, it goes away.
And what is the monoidal operation in this?
So K is the tensor. K with, when you have a K and an R and you run the thing, right? That's when you get that. So let me go back to the PDF here. Okay, so when you make the cut, supply the R, and now you can run this bit, and you can run this bit, and then you can run this bit. That's the idea.
I see. Yeah.
Yeah.
Okay.
And since you're given that these are of type perp, you'll you know that so this one wires up T1 to T3 and T2 to T4, which is a parallel wiring, as opposed to a series wiring. But because you know that T is of tau 1, T1 is of tau 1 perp, and T3 is of tau 1, then you get that they're then you know that they're going to go, this combination here is going to go to go to the RK. And likewise, T2 is of type tau 2 perp, and T4 is of type tau 2. So this combination is going to go to the RK. And then when you have a K of an K of an RK and an RK, well, that's the identity, so it's just RK. So you just have RK, so you have R of RK, and that's why this type is that way. But the type system is guaranteeing that it runs to completion. It runs to here. So you can think of whatever property we give it, and it doesn't just have to be RK. It's just any old persistent property, right? So it's got to be the case that K of the property and underscore, so K of some property which we're going to represent as a persistent process, and something else, whatever that is, has got to be the something else. So for example, par of P, a bang P together with P is the same as bang P.
Yeah.
So it makes, so it's a yeah, so you have to look at these persistent properties, and what this guarantees is a kind of isolation or non-interference, right? Whatever you're doing over here doesn't interfere with what's happening over here, which is exactly the kind of property that we'd like to have in a blockchain, right?
Yeah.
All right, so this gives us the kind of isolation that says it's safe to run these transactions in parallel.
Yeah. So if we think about more specific, for example, in lambda calculus, these are two applications that are not
that won't
connected.
step on each other's toes. That's right. Or
Okay.
in the case of pi, those are two parallel compositions that won't step on each other's toes.
Okay. Yeah.
So it's totally safe to run them simultaneously. So this will, so when we feed this into our chain, this gives us all kinds of useful data, right? The contract is safe. But it's at this level of generality, right? So this is, you can apply this, again, we haven't said which specific execution model we're using. It's just that it has to meet these axiomatic criteria, right, which we've laid out up here. Right, so here's the minimal, let's see. So we have a kind of minimal axiomatic criteria. So you've got, you've got some constructors of this kind, you've got some rewrites of this kind, and you've got to have at least a left or a right identity, one or the other. If you have both, they have to coincide algebraically. And then once you give us something like this, then we can build the resource theory, which says we're going to basically interrupt this thing, right? So here's the gas. You give me a term, and I give you a new term that has the gas made available. And then there's a par term, which is going to be used to extract things that are stuck in here without gas. And that one's, you extract them in parallel, and this is you extract them in series. And then we also add this notion of context. It looks scarier than it is. It's just, we're just adding this idea of a one-hold context, which you can think of as like a linear lambda. So you can introduce a hole, and then you can put the hole on the left, or you can put the hole on the right. You can make a lambda-like thing out of a hole on either the right or the left-hand side, and then you can and then there's applications and substitutions, and that's basically all that's going on. But once you have that, then you can give this rely guarantee kind of type. So if I can rely on tau happening, then I can guarantee that tau prime happens. And then there's a left and a right version, because K may not be symmetric, commutative. And that's it. That's the whole thing. And then that gives you so basically the proof rules come into two chunks, right? There's sort of what we might call the multiplicative chunk, and then there's the additive chunk, and the additive chunk has to do with context. The reason, even though a context doesn't show up here explicitly, because we're using these rely guarantees in the types, the series composition. So the trick is that you have, in order to have things work in series, you're going to whack you're going to whack T1 against T2. Okay, so that's, you take T1 against T2, and you take T3 against T4. So T2 is of type tau2, but T1 has to take a tau2 and produce a tau1 perp. Okay, so when I put one of these into here, that's this, sorry, you can't see when I put one of these into here, I get one of these, right? So I put, so here's that composition. So this is going to go into here, right? And when this reduces, it's going to result in a tau1 perp. So this whole thing, this whole chunk here, oops, this whole chunk, I don't know why it's being like that. This chunk here is all just going to be a tau1 perp. And then over here, I put one of these, which is a tau 3, into something that requires a tau 3 and produces a tau 1. And so now we get a tau 1 for this whole thing, right? So we have a tau 1 perp and a tau 1. So we know that that reduces to an RK. So that's, so you can see that we needed this error, this rely guarantee is at the type level. So that means that this thing has to be a lambda, even though it doesn't say that on the surface. So that's why all of these rules are grouped together. These rules all involve context, and these rules all are context free. They're done without context.
Okay.
Yeah, that's the idea. So anyway, but this I'm quite excited, right? Because this was the other piece of the puzzle that I hadn't thought about, but it's there. We have a we'll end up with a traced gadget. So we'll have to spell out exactly what the trace is, and that tracing is quite lovely, right? This sort of completes the Abramsky interaction program in a certain sense, because we show, all the ingredients you need in order to make this work quite generally. You have to have the reflective structure. You have to have the control, the gas control thing, and you automatically get the trace. So.
And this trace can help us in the replay, or it's...
So that's an interesting point. I've been thinking a lot about this. So the issue is the parameters in the IO that have operations on them. So whenever you have things that support an addition or a multiplication or something like that, where you lose information as you go forward in the computation, you can't just use the modalities. You have to use the modalities and other information. So, but you can run the thing backwards. So you can say, what is the final state? And then you start with the last COM events in the graph, right? Whatever's applied from the previous state to this one. And you apply those, and you say, can I get to here? And you can do it that way. You can run them backwards.
And how can we do it with random generator?
You don't need the random generator.
Okay.
No, sorry. The random. What I mean is, you're given the sequence. You're given the trace, right?
Yes.
Trace not in the sense of trace monoidal category, but trace in the sense of execution trace.
Okay.
So you're given the thing, the context stuff, and you're given the execution trace, and so now you could work backwards. So rather than play it forwards, run it backwards, and that might be a little bit more computationally efficient.
Yeah.
right? But the I mean, what I think we really need to do is you want to transform the problem into a something more topological or even better geometrical, so that you only have arithmetic operations to check. But I don't know that will be that the problem transformation won't be hard. So let me give you an example of what I'm talking about. So let's say that I have I'm gonna give a problem, right? And the problem is, if I have a circle of radius r and I increase it by r delta, what's the overall increase to the circumference? Now we can go through the arithmetic to to figure it out, but you can see it really easily if you were able to convert the circle into a square. Then you can see that the r the imagine extending the sides of the square, right? Then the sides that you had before, they make up a certain amount, and then there's the corner bits.
Yes.
Right? And those corner bits are going to be exactly a delta on each side. So you'll get 8 delta, right? On each corner you have 2 deltas, and there's 4 corners. Yeah, and that's the answer. It's always 8 delta, no matter what. Right? No matter what delta is. But it turns out that squaring the circle is impossible. You can't constructively square the circle. So the problem so even though, like, when you the answer, the visualization is quite obvious, handing you the problem in the original format and getting it into the other format is quite onerous. So I have to prove, so there's a proof obligation that the transformation of this verification problem into a kind of geometric format isn't at least as complicated as executing it in the first place.
Yes.
So just just to recap what we said with respect to replay, if we didn't have to worry about functions in the value positions of COM events, then we could definitely win by there's for any trace, there's a corresponding modal formula, and you can check that the process satisfies the modal formula.
I see.
Right?
Yeah.
That but the issue is that when you run it forward, if you have functions of values in the outputs of subsequent events, and those functions are not reversible, then you have a problem because you don't know how those values arose. In particular, someone could be hiding a double spin in the way those values are combined. So one approach is to flip that check to to something that is geometric. So you want to ask, you want to ask it something like, is the that's interesting. Is the step from one state to another bigger than continuity would allow? So you want to think of each step as like a transformation on an R ball, a ball in some n-dimensional space of radius R, and you want to ask is and so essentially every step is a transformation on that ball, but we're insisting that all computation, all legal computation is somehow continuous. So any transformation on the ball has to be a continuous transformation. And if one of those steps is not continuous, then you'll see the discontinuity in the transformation. There'll be something that like tears the R ball or takes a point outside of the R ball or something like that.
So when you say continuous, you mean allowed by the semantic rules?
That's right. That's right. So what we're saying is that continuity is computation. So that's the insight of Dana Scott, right? So Dana Scott's semantics for the land of calculus boils down to this one idea, which is that continuity in the sense of topological continuity, right? So opens come from opens, is equivalent to allowed computational steps.
Yeah. Can we use this model formula and somehow store all the places where we are using this non-reversible function calls, so we can check these points together with the model formula?
Well, that's a thought. It's a thought. I have a feeling that ends up being just as hard. That's the problem.
Okay.
Here, that's the same as executing.
Oh, I see. Yeah. But you are saying that it is possible that we are verifying in opposite direction.
I think that might save us something. That might save us.
Okay.
Yeah.
And I was thinking about reducer and how to guarantee that this reversible reducer is the same as reducer. It would be nice that we can prove this and say this is the same thing, and we will not have bugs, like strange bugs, because we have two different codes.
Yes. Yes.
It would be nice that we can have only one reducer and somehow run it backwards and supply it and say you must go in that direction. So if this is not continuous, we can just say, oh, this is false execution. I mean, we have two different sources. On one side, we have the code that we need to validate, and we have the trace. And we don't want just validate the trace, because this can be fake. So in each step, we need to validate code against the trace. Right.
Yeah. Yeah. I mean, another possibility is to try to see if there's some variation of ZK snarks that might apply.
And these ZK snarks, they want to have this private. computation, but we are not care about that, right? So we don't need this complexity, maybe.
Yeah, I think that's probably true. All right. Well, with that, I need to get ready before the stand up. So I'm going to jump off here. But thanks to everyone. I appreciate it.
Thank
Yeah,
you.
thanks, Greg. We appreciate it.
Cheers.
See you. Bye bye.